Hello and welcome. In this video lecture, we are going to talk about the most expressive description logic language family, that is Shrike. Right. Now, by the name, we already understand what are the kind of constructs that it allows. Let us try to talk about what are the kind of constructs that are relevant in this language family. So as we have S, so you know that all the constructs from ALC, right, constructs plus the role transitivity. This is allowed. Transitivity. By R, the generalized role inclusion is allowed. By O, we allow the nominals, right? By I, we allow the inverse of role, inverse of roles. And by Q, we allow the qualified cardinality restriction. Right. Now, looking at the types of statements that this Stoic family has. So earlier for ALC we have seen, in ALC we have seen that there are two types of boxes. One is the T box, which contains the terminological knowledge, and we have something called A box, which contains the assertional knowledge, right? So we could have done the same for Stoic family, but looking at the level of detail in which it works on the role or the roles and their relations among the different roles, the T box is separated into two other more subcategories. One is R box and the T box in the simple sense, right? So the type of statements in Stroik, it contains statements. One is the T box. Basically, it will contain all the statements or the axioms related to classes. So it contains all the axioms related to classes. So basically it contains a set of GCIs, generalized class inclusion axioms, right? Uh, Next we have something called R box. R box is basically the axioms related to roles. That's why it's called the R box, and it basically contains role hierarchies and generalized role inclusion. And finally, we have A box in the traditional sense. It contains all the assertions related to class membership and role membership, right? Now, we know already what we mean by T box and A box, so we are not going to discuss them for sure. But we have a special interest in this R box. The composition of R box, the constraints over this R box, they are very important to us. So as we talk about this, R box really contains the generalized role inclusions. But if we allow arbitrary generalized role inclusion, that will make the language family undecidable. And we always want to have something which is decidable, right? So that's why this R box is a kind of having this generalized role inclusion and the role hierarchies, but there are certain constraints that are put over this R boxes, and that's why this R box is the most crucial thing for this week, and we need to spend some time on defining what is the R box of this Shriek language family. What are the constraints that are imposed over these R boxes? That will give us a better view of what are the kind of constructs that this Shriek family can have in addition to these T boxes and A boxes, right? So let us try to dig into detail on the stoic R boxes. So if we look at the stoic R boxes, uh, it contains atomic roles, and these atomic roles, they can be simple role names. They can be simple role names. So role names are basically say has parent, has child, has brother, something like that. And we will be representing that with R, right? And we can have inverse of role. So these are all atomic roles, inverse role. So this simple role or the role name, so we will be using this term, role name and inverse role. So they will be represented via R and R inverse, right? And in addition to that, we have something called top role, right? And top role will be represented as U, right? And apart from having these atomic roles, the Stroik box, R box, contains something called generalized role hierarchy. Generalized role hierarchy, right? And this one form of this generalized role hierarchy is called generalized role inclusion axiom. Generalized role inclusion axiom, and this role inclusion axiom will be referred to as RIAs, right? And the special form of this role inclusion axiom or generalized role inclusion axiom is basically role composition via property chain, right? So this particular form of this role inclusion basically forms the basis of R box of this Shroik language family, right? So what we say, the role composition, this role composition is the basis of RIA in Shroik. So let us try to look at different forms of this role inclusion via role composition, right? So let us first take an example and try to formulate that as composition of different roles, right? So the example goes like this: if someone owns a car, and uh, the car has an engine, then the person owns the engine, right? Now how to encode that bit formally? So let's say P1 is the person, owns say C1. So this is the kind of relation that we know to be true, and C1 has part E1, which is the engine, right? Then we say that P1 wants E1, right? So basically we are having two relations and we are composing two relations. So the composition will look like this: won, then has part, and this will imply that this P1 owns E1. So this is a kind of chain that we are following. So P1 then owns C1, then C1 has part E1, and that will say that we will try to kind of derive the fact that P1 owns E1, right? And this is what we call as role composition. We are composing two roles to get another role, obtain another role, right? So let us take another such example, right? So the example goes like this: if a disease affects a kidney and kidney say is part of the renal system, then the disease basically affects the renal system. So this is a very common sense knowledge, right? And this also we can represent using composition of different roles, right? So the roles that we have affects and say is part of, and from that we are obtaining affects, right? We are saying affects compose say is part of, and this will imply affects, right? So basically we need to look at the kind of individuals that are appearing as subject for this relation and object for this relation, and they will be, so for example, x and y, right? So if x and y they are connected via this composition, then x will affect y. So this is the kind of semantics that we can associate with this composition of roles, right? So if we try to generalize these kind of statements that we have seen earlier. So let us try to rewrite the statements that we have obtained. So wants, then we had got say has part, uh, has part. This implies wants, and then affects is part of implies affects, right? We can try to generalize this by saying that we have to have something like this: R composition S uh, implies V, right, in a generic form, right? So where this R, S and V, they are the role names or role inverses. So for example, I can just convert this to be say uh, affected by, then uh, has part, mm, and then it will be something like affected by. Let us see we have the similar kind of semantics or not. So kidney is sorry, so we should write something else, not this one. So we can have something like this, say has part then affected by will imply affected by. So the renal system has part kidney. Kidney is affected by a disease, then renal system is affected by the disease. So these are kind of inverses of these two. So this, the point that I'm trying to make here, that this R, S and V, they can either be role names or they can be inverses, right? Now if we, so this is kind of called one role inclusion axiom or RIA, right? And your R box is a set of all such RIAs, right? Now this is a very generic form of this RIA, and if you have this kind of RIAs, then your language system becomes undecidable. System is not decidable, and that is not a really a good news, right? So that means we cannot have a very unrestricted form of this road inclusion axiom. So we need to impose restrictions to ensure decidability. So our task would be to restrict the forms of RIAs to ensure decidability. Right. So let us take the first step towards ensuring decidability. So we'll be taking different measures to ensure decidability. So this is the first measure that we are talking about. So ensuring decidability 1. So this is the first strategy towards ensuring decidability. Right. So the first strategy says that we 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 can apply impose we can impose certain restriction over the forms of arrays, over the forms of array, right? Now let us have a look at this. So here you can see that both this wants has part won and affects is part of affects is of this form. So R composition S and this imply R. So I'm just replacing this owns with R and has part with S and this owns with R, right? Here also we are replacing affects with R, has part with S and affects with R, and both these will follow this form, right? So this is a kind of restriction that we are imposing, that this should be the form of RIA to ensure decidability. I will not talk about the proof for this, because that will get into very involved analysis of the things, but we'll just take out the result from the description logic research community that this kind of form will ensure decidability, right? Now a corollary for this would be if we take the inverse of both the sides. So we are taking inverse of R composition S and the inverse of R, right? Now we have already talked about the inverse of these affects, right? So again, let us write down the inverse of. So we are taking the inverse of, say, owns, inverse of owns as part and imply inverse of ones, right? So when we take the inverse, the position of these two relations in the composition will be reversed, right? So we'll be having the inverse as a result. We'll be having the inverse of has part first, and then we have the inverse of ones. Otherwise the chain will break. If you don't flip the position of these two properties while you take the inverse, the chain will break. You can try it out, right? So we'll have inverse of ones, right? The inverse of has part is part of, right? And the inverse of owns is has owner, right? And this brings us to has owner. So you can think this is part of to be equivalent to say is prime. Then you can think of has owner to be r prime, and this has owner to be r prime. So what are the kind of forms that we see here? So what are the kind of allowed forms we can see here? So this is the restriction one. So the Ri is should be either of the following forms. So one is R composition S implies R, and S composition R implies R, right? So this is the first condition that we are imposing, and that condition is imposed on the form of the RIs that can take, right? Now we talk about the second strategy for ensuring decidability. So ensuring decidability 2. Ability 2, right? Now let us consider a case where we have two role inclusion axioms in our R box, and the two are R S and S implies R. So this is following the earlier form, so there is no issue in this. But you see there is a cycle. So from R you go to S, and from S you go to R. So you see there is a cyclic dependency. And it might so happen that the reasoner will go on into an infinite loop, because we have a cycle here, right? So to ensure this, and that will make the system undecidable, because we cannot have our answer within a bounded amount of time, right? So this is the restriction 2 that we are imposing. What is the restriction? That the Ri is they have to form an acyclic R box. So an R box that does not contain a cycle, and this cycle will be indicated if you have a form like this. So this role depends on S, and this S depends on R. So you have something R depends on S. So if you say depends on S and S depends on R, right? So if you have this kind of scenario, then your RIA is cyclic, and you want to make sure that your RIA is not whatever the set of RIAs you have in your R box is not cyclic. In a sense, it should be acyclic, right? Now the question is how to check for acyclic. So how to check for acyclic? So while you are creating or developing your ontology, so as you are developing your ontology in different times, so you are not creating this ontology at a single go. You are doing multiple iterations, and of course the ontology can be created in a distributed way. Multiple people, they are collaborating with each other to create the ontology, and as a result you might be having one RIA or R box which is a cycle. So while you are debugging your ontology and trying to see whether you have satisfied all the constraints that are there or restrictions that are imposed over the constructs, so you need to check whether the R box is acyclic or not. So we need to see how do we really do that, right? So for that we need to think of something like this. So here you have a case like R. It affects, by the first statement you see, we can say that R affects S, right? Now S might affect another, right? Affects say say P. Now at the end P might affect R. So in that case you have a cycle, right? So whenever you have something like R to S, R implies S, or R is a sub-property of S. So that means we can say that R directly affects S. Now, if you have something like that, S affects or S is sub-property of P, then you can say that R affects directly affects, I'll say directly affects S, and S directly affects P, and we can infer that R affects P. From this, I can infer that R affects P, right? And if we see that R through a path affects itself, then we have a cycle, right? So that's why we need to ensure that we do not have such a path that will start from one relation and again end up into that relation. So we need to check whether you have a situation like this, right? So let us define what do we mean by directly affects and what do we mean by affects, right? And that will give us the sense of cycle or acyclic nature, right? So we define a role R to directly affects. So R directly affects some other role, say S, and this always with respect to one R box, right? First of all, this R should not be equal to S. So these R and S, they should be different relations or roles, and it should satisfy the following condition, right? So the first condition is that you have a hierarchy of relation between R and S to be R is a sub-property of S. So if that is so, then we say that R directly affects S, right? Or we have a form like this: R composition S is a sub-property of, then also R affects S, right? The third condition is if you have something like S compose R will bring us say S, right? Then also we can say that R directly affects S. right? So with this definition of directly affects, let us define the affects relation, right? So we say, so we will be representing directly affects, we will be representing directly affects with symbol something like this. So this is a kind of special arrow that means R directly affects S, right? And this will happen when if either of these three conditions is satisfied, right? Now, in order to define affects, so affects is basically, we are defining affects. So affects is basically a transitive closure of directly affects. So it will be, as we have represented it, it will be represented like this, and affects will be represented as this symbol, with this symbol. So these are all arrows because they are directly directed relation, right? So what we mean by this transitive closure? So let us see what we mean by. So we have something like R1 directly affects R2, and R2 directly affects say R3, and so on and so forth. And finally, say Rn minus 1 directly affects Rn. So that will imply that R1 affects R2, R1 affects say R3, and you can say that R1 affects Rn, and you can have other relations like say R2 affects Rn or something like that. So basically you have a chain, right? So from R1, this R1 directly affects R2, R2 directly affects R3, and you have something like this Rn. Now we say that R1, so these are all directly affects. And the transitive closure is you have one count relationship which is affect. R1 affects R2, R1 affects R1 affects R3, R1 affects Rn. So this is what we mean by transitive closure. Okay. So basically this R1 affects every other relation you have if you have a chain like this, right? Now, how do we define one acyclic R box? How do we define one acyclic R box? So if there is no role, so if in the acyclic R box, if there is no role that affects itself with respect to the R box, then then the R box is acyclic. So let us have an example, the example that we are working with, right? So let's say we have something like this. So bones as part is a subproperty of bones, right? And let us have something like this for the sake of example. Bones as part as part. This might have no real meaning, but for the sake of example, I am using these two role compositions, right? So by the first RIA, what we can draw, we can say that has part has part directly affects, or in the sense affects wants, right? And from the second relation we can say that wants directly affects has part or affects has part. And you see we have a cycle here. So this is not a cycle. So this is not a cycle. Right. So with respect to uh, having the role in or the R box to be acyclic, so let us see what are the allowed RIAs in Schroek. So the allowed RIAs in Schroek to ensure acyclic. Right. The first thing that we need to have that we can have more generalized form of RIAs. So what is the form that we can think of? So S1 composition S2 composition Sn imply R is a subclass subproperty of R, right, where n is greater than equal to 1, right. And this Si can be a role name or a role inverse. So this Si can be a role name or role inverse. But this R should always be a role name, not an inverse. Be a role name. But these SIs, they can be either a role name or a role inverse. So the example of this sort can be something like this. Say has parent, then has sibling. If we compose and we compose it with say has parent inverse, then we can get the relation like has cousin. Right. Now let's say this is this RIA or RIA1 is included in your R box. So this is already in your R box. Now in presence of this RIA in the R box, you cannot have another RIA which is say of this form. So any chain followed by has sibling, followed by has sibling, and then followed by any other chain. It should not get us to has cousin. So it should be other way around. We should not have something like say as cousin and as sibling. And this is required in order to avoid to avoid cyclic dependence. Right. Now the second form which of RIA which is allowed is that it concerns the placement of the RHS role in the LHS role composition. So I'll be giving example, but before this, let me write down the uh, proper case. The case is the placement of the RHS role in the LHS role composition, right? So this is the restriction that we are imposing. The restriction is that the RHS role can occur either at the beginning or at the end of the role composition in the left hand side. End of the LHS role composition, but not at both the ends. Not at both the ends, right? So for example, this is allowed. Say for example, S1, S2, then composition R. So this is allowed. So this is the left hand side. So this is the right hand side role. So this is the role name that appears in the right hand side, and it is only a role name. It is not an inverse of any role, right? And this is appearing at the end position of the role composition of the left hand side. So this position is the end of the role composition of the left hand side, right? So this is allowed. So one example of this is, say, has engine, then has part, and say has owner. This composition is a sub property of has owner, right? Now if you take the inverse of this, right, if you take the inverse of this, so it will become R inverse composition S1 inverse, sorry, Sn inverse, Sn minus 1 inverse, go on like this. Then we have S2 inverse, S1 inverse, and this would be inverse of R. So if you take the inverse of this concrete example, what would it become to? So is owner of then composition is part of and then engine of, and this will imply that is owner of, right? Now let us replace all these inverses with say in a different form. So we make this R inverse to be equivalent to be R prime, then S2 inverse to be equivalent to S2 prime, then S1 inverse to be equivalent to S1 prime, and this will become R prime. So you see, the role name that appears in the right hand side, this is this appears in the first position of the role composition in the left hand side. So this is the case where the the right hand side role name appears at the end position, end of role change, role composition. And here this right hand side role is appearing at the start position of the composition. but not in both, right? So this is one constraint that we need to follow. The third constraint that we need to follow, which is basically the exception of two. So there is an exception of two, and this exception is valid for the role transitivity. So how do we define role transitivity with respect to role composition? We can say R compose R, it will become R, right? Now here see that we have the role name R, which is appearing at the right hand side of the role inclusion axiom, and it is appearing both at the start and the end of the role composition of the left hand side, right? But if you don't have this, you cannot model role transitivity. So this is allowed only this form where these two roles are appearing both at the first position and the last position. This is allowed if you are modeling something which is called role transitivity, right? And the fourth constraint that we like to have, which concerns the case of symmetry. And here we can have one inclusion like R inverse is uh, is a subclass of R, right? And if you want to make it symmetric, R is also a subclass of R inverse, right? So these are allowed to allow the case of symmetry, right? Now let us try to revisit the case of ensuring the acyclicness. So we are trying to revisit the case of ensuring acyclic, right? Now what we are doing now, we are trying to really disallow the cyclic RIS. So we are trying to disallow cyclic RIS, right? And how are you ensuring this? So basically, each SI that is appearing in the left hand side, that is appearing. So we need to really model the directly affect and the affect, right? And we need to have a mathematical description of that, right? So that's why we are revisiting this acyclicness, ensuring acyclicness, right? So this each SI, this appears that appears uh, in the LHS, this should be coming before the role that is appearing in the right hand side. So they should be coming before the role R in the RHS. So we have a sense of ordering. So this SI is coming before R. So that is the kind of ordering that we are talking about. So that ordering, we are representing that as a partial order relation, right? So this means that SI has appeared before R, and what is the constraint? That we have something like this: S1, S2, Si, then something, and then you have R. So you say that in that case, we say that Si comes before R, right? So basically, we are modeling with this. So this is a partial order relation, and with this partial order relation, we are modeling the directly affects, right? Now, what is the kind of constraint we have on this operator, this partial order operator, this partial order operator. This partial order operator is a strict partial order operator. What we mean by that? If Si comes before R, if this is allowed, if this is there, then do not allow R comes before Si. So that's why this is a strict partial order, right? So the order is from Si to R, not from R to Si, right? So this strict partial order is basically a binary relationship. It is a binary relationship which is transitive and irreflexive. So that means you cannot say, so if we just look at the irreflexive case, you cannot say that S comes before S or Si comes before Si. You cannot say that. You cannot have a pair which is a kind of instance of this Si, that kind of thing, right? Now the case of transitive says, why this is a transitive relation? Transitive. Why this is a case of transitive relation? Because if S1 comes before S2 and S2 comes before S3, that will imply that S1 comes before S3. So what it is modeling? This is basically modeling the affix relation that we have talked about earlier. So if we have a single chain here, as we have here, right, Si comes before R, so this models directly affects. And if we have if we can combine multiple such chains, so that will bring us to the transitive transitivity in the directly affects relationship, and the transitivity will imply the affects relationship between two roles. So if S1 directly affects S2, S2 directly affects S3, then we can say that S1 affects S3, right? Now, by defining this strict partial order, we can define the regularity of an R box. So we are trying to define the regularity of R box. So basically, we will try to find out or ensure to have an R box where we do not have any violation of this strict partial order. So that is the kind of R box that we are looking forward, right? So this is an R box that does not have any violation of the strict partial order, right? So we say a role hierarchy or R box is regular if there is a strict partial order such that the first condition is that if S comes before R, so the same will be valid for their inverses. So the inverses, they should also follow the similar partial order. Right? And the second condition is that every real role inclusion axiom, so this is the most important. So every role inclusion axiom, let me write down RIA for this. Every RIA will be one of the following forms. Right? The first form it will allow is the case of transitivity, which is R compose R is a subproperty of R. Right? So if R compose R, then it will imply R. Right? Has ancestor, compose has ancestor, then we'll be having has ancestor. Right? The case of symmetry. So the R inverse is a sub set of R, a subproperty of R. Right? So this is the case of symmetry. So either this, or the third case is S1, S2, then Sn. This should be the subproperty of R. So this is the general case, right? Or you can make use of R in the left hand side in the composition, but it will be restricted by the position of the start or the end, right? Either it can appear at the start or at the end, but not in any arbitrary position apart from start and end. So the fourth form is R compose S1, compose S2, then you have say compose Sn. It will bring us to R. Or the fifth form is S1 compose S2, compose Sn, compose R will be a subproperty of R. Right. So where R is a non-inverse role name and there is a strict partial order between Si and R for all I equal to 1 to n. Right. Now with this definition, let us take two examples and check whether the examples, which category will they belong to, whether they are regular or irregular. Right. So the first example that we like to have is say is a proper part of, and let us try to make this to be a subproperty of is part of. Then we have say composition of is part of, composition is part of, and this is a subclass of is part of. So this is the case of transitivity, right? Now you have something like is part of, then is proper part of, and it will be a subproperty of is part of. The fourth one is proper part of, compose is part of, subproperty of is part of. So this is one example. The other example is has parent, compose has husband, uh, implies has father, right? And has father implies has parent. So these are the two examples. Now let us try to examine whether each of these examples whether they will be regular or irregular, right? So let us try to translate them into more simpler form. The first relation can be translated into, say, let us replace is proper part of to be R and is part of to be S, right? So R implies S. So this is the first relation. The second RIA can be converted into something like S compose S, a subclass of S, right? The third one can be rewritten as S compose R, and you have S here. Now you see here we have one strict partial order to be A R comes before S, and you have a strict partial order here to be R comes before S, right? And the fourth one can be translated into uh, um, the R compose S to be S, and here also we have a strict partial order to be R coming before S, so we do not have any violation, right? And all the forms that you can see, they are following one of the forms of this 1 to 5, right? So that's why this is a kind of regular R box. So this is one regular R box. Now coming to here, let us replace has parent with, say, R, and has husband with S, right? And we have something like, say, this to be V, and it is violating from the very first place that it is not following following the form of allowed two forms, right? So the allowed two forms was R compose S to say R, and S compose R to R, something like that. But these are not being followed. So we have got three different role names in three different places, right? And the second one is, so but again here we are having the relationship between R and V to be R comes before V, right? Now here in the second place we have got, say, V to be a subproperty of, say, R, right? And here you are having a strict partial order to be V comes before R, and here you can see that it is violating the definition of strict partial order. So that's why this is a case of irregular R box, and this is a regular R box, right? Now let us come to the third point of ensuring decidability. So the third point of ensuring decidability, D, right? Now till now what we have discussed, the constraint over the role inclusion axioms, right? But also while we are creating class expressions out of the role names, there also we need to put restrictions to ensure uh, decidability, right? So we need to impose restriction over the class expressions used to create another class expression to ensure decidability. So for example, what kind of scenarios you can think of? So Let's say you have something like this: for all R C. You can have for there exists RC. You can have for all RC. You can have less than equal to NRC, greater than equal to NRC. So these are the kind of, we are using roles here, right? We are using roles here, but we are using also certain class expressions that are kind of will be the class for the values these properties will take, right, for a given subject. Now, depending on what kind of expressions that you are using here, or what kind of roles that you are using here, uh, mm, I will not say restriction over the class expression, restrictions over the role, right? So you cannot use any arbitrary role expression here to create this class expression, right? So you need to put some restrictions on them as well. So this is what we will be following. So the roles used in certain class expressions should be simple. So let me write this simple thing in caps. Simple. But we haven't defined the notion of simple roles, right? So let us define the notion of simplicity of roles. Simplicity of roles. So role R will be called simple if neither R nor R prime appear on the right hand side of any RI in the R box. So this R or R bar, which is inverse, does not appear in right hand side of any RIA of a R box. In that case, R and the R would be a simple role, right? You need to check whether both this R or R prime does not appear, right? Now the second case of simplicity, so if we call a kind of role to be simple, R to be simple, if R is simple, then the inverse of R is also simple, right? Now the third case of simplicity says that R appears in the right hand side of a form like S is a subproperty of R, right? So you see that R is appearing in the right hand side, and then R will be simple if S is simple. So if R appears in the right hand side of our role inclusion axiom, then also R can be simple provided S is also simple, right? So let us take an example of R box. So the example says that we have, say, R is a subproperty of R1, R1 compose R2 is a subproperty of R3, and R3 is a subproperty of R4, right? So what would be the simple roles? Set of simple roles. Now let's look at R. So R does not appear in any of the right hand side of the role, or R inverse does not also appear in any of the right hand side of any of these RIAs. So R is a simple role. Now as R is a simple role, R inverse is also a simple role. Now let us take R1, right? So R1 appears in the right hand side of a role, but the left hand side of the role R, R is simple. So in that sense, R1 is also a simple role. And as R1 is a simple role, R1 inverse is also a simple role, right? Now take R2. R2 appears in the left hand side of the RIA, right? And it does not appear in the right hand side of any RIA. So that's why R2 will also be one RIA, simple role. And R2 inverse, as R2 is one simple role, then R2 inverse will also be a simple role. Now take R3. R3 appears in the right hand side of a role, and the left hand side is not a form like S to R. So that's why R3 will not be a simple role. As R3 is not a simple role, R4, which is appearing in the right hand side of this form, will not also be one simple role. So the same set of simple roles for this R box would be R, R inverse, R1, R1 inverse, R2, R2 inverse, right? Now, whenever we are creating uh, different role expressions or complex class expressions using the role expressions, so in that case, only simple roles will be used in whenever we are trying to define a role to be irreflexive. So we cannot really define a complex role to be irreflexive, right? And whenever we are trying to define two roles to be disjoint with each other, then these two roles, they should be simple, right? Now the simple roles, they can only be used to assert uh, uh, negated facts, and those are called negated role assertion, right? Third thing is, whenever we are using number restriction, right? So this simple roles, they can be used only in number restrictions. We can use only simple roles. So for example, less than equal to s q, right? Or greater than equal to n s, something like that, right? And also, while we are having self restriction, right? So we are defining, so this is the case of reflexive property. We are defining a property which is reflexive. So in that scenario, we'll be using only the simple rules, right? So let me stop at this point, and in the next lecture we will be talking about the set of allowed constructs in Shroik in the light of the discussion that we had uh, concerning ensuring decidability. Then we'll be coming up with the model theoretic semantics of Shroik as well as the first order logic representation of Shroik. Thank you very much.